see how can you handle all the constraints and how to change them using the IP-opt library. Just to show you, for example, how this works for the minimization of the area under constant width constraint. You can see that you quickly converge to the Reuleaux triangle, and this is the optimization for the theoretical Laplace eigenvalues. Also under constant width constraint, it's really fast and it works really nice in FreeFEM. Okay, so the objective is to be able to extend the framework in 3D. The problem is not FreeFEM; it's just how to find the proper parameterization that you can easily do in FreeFEM. And the convexity constraint is not so simple in 3D, but that's for some other time. And now let me show you a second application, again using the capabilities of FreeFEM. When you are trying to optimize some things related to optimal partitioning problems. And this came from an article on Images de Mathématiques, and the problem was to see which shape maximizes the minimal relative perimeter. Now let me just tell you what is the relative perimeter. If you have a set big omega and a subset, you would like to count only the perimeter of the subset which is inside the omega. And if you look at the minimal relative perimeter, you minimize this type of problem where you have you minimize the perimeter with a volume constraint, and you obtain shapes, optimal shapes, which are in gray here, that are of this form for various constraints C. And the problem was to find the domain omega, so the big domain, which maximizes this minimal relative perimeter set. And there was a paper that did this only in 2D for C equal to 1/2 from the theoretical point of view. And we asked ourselves, how can we do this numerically to test what happens for various proportions of C? And also, since we know how to do this numerically, we can ask also the following questions. How do you maximize the minimal perimeter of a partition? So which is a slightly more complex problem than this one, again with given constraints on the cells. Let me just show you how we deal with this problem using FreeFEM. The idea is that in order to compute minimal relative perimeter sets or partitions, we don't want to work with sets with cells of the partition, but we use a relaxation of the perimeter by gamma conversions. The idea is that we approximate the perimeter by a functional which depends on a density. And in this way, we pass from a shape optimization problem to a functional optimization problem. And the volume constraint is just a linear constraint on the density. And in practice, we just, for one phase, we minimize this problem. And you can see that you have one term with weight 1/epsilon, which will force your density to be a characteristic function, and one term which looks at the gradient and will, in fact, count the perimeter. And for the partition case, you just sum this kind of functionals for all the densities. Now, in FreeFEM, the computation of this functional is not hard. You see that you have the integral of the gradient square, so this can be computed using the mass matrix, and you have an integral of the density of a certain function of the density. This can be so this can be done with the rigidity matrix, sorry, and this can be done with the mass matrix. And you can obtain explicit formula when you pass to the expression in a finite element space, and this is the formula that you obtain. And for this formula, you can compute the gradient with respect to the density variable u, which will be a vector. So you can compute the derivative with respect to every component of the vector. And you need to handle the constraints, but this will be just linear constraints. The integral constraint can be can be expressed using the mass matrix, and the sum constraint is just an algebraic constraint. Now, just to talk just a bit, how can you project on this constraint? The idea is that you take your density ui and you try to find some multipliers, lambda and mu I, such that, well, when you make this modification, you would like to preserve the volume constraint and also the sum constraint, and you do a bit of computation and you find explicit values for lambda and mu I. And if you do the projection on the gradient instead of doing it on the densities, then you can use a black box optimization software like NLOpt in FreeFEM, and you can perform efficient optimization for this problem. So the idea is that you project the initialization on the constraints of a given area and given sum, and then the gradient you will project on the equality with 0 everywhere. So when you change your density, you won't affect the constraints. Now, just to show some examples for a fixed domain omega. So here you have an example where you minimize the relative perimeter, and here you have some partitions for 2D surfaces and 3D. And for initialization, for one phase, you take something random and you just run it multiple times to get rid of local minima. And for the multi-phase, you can use Voronoi diagrams. In 3D is also some random and multiple runs. Now, we said that we want to maximize the minimal perimeter of a partition. And we know that we only managed to prove that the existence holds for convex domain. So we consider some radial parameterization of the shape. In 2D, we consider a straightforward expansion using Fourier series. And in 3D, we use a parameterization also using a Fourier series in the two angles. But for meshing constraints, you need to have this parameterization be constant for the angle phi equal to minus pi or pi, because otherwise FreeFEM won't be able to build the mesh with move mesh surface. Then using again the shape derivative, you can obtain the derivative with respect to each one of the parameters and use a gradient algorithm. Now, in order to build the mesh in 2D, that's easy because you just use build mesh with the radial parameterization. In 3D, I just started from the example in the documentation for the surface mesh of a sphere and find the parameterization, 3 functions which define the parameterization, then the metric, which is used for a 2-dimensional adapt mesh, and then you move this mesh in 3D to find your radial surface. And so you have the surface mesh, and in order to have a 3D mesh, you just use that gem, which is very nice. So the advantage in FreeFEM is that after you do the mesh, after you construct the mesh, the code is practically the same in every dimension, 2D, 3D, or surfaces. Then, as I said, you solve the optimization problem for the partition or the finite or the minimal relative perimeter set on a fixed mesh that you have constructed using the NLOpt LBFGS software. And well, I just described previously how you compute the objective function and the projections on the constraints. Then you need to update your shape in order to increase the objective function. We said that we want to maximize the minimal relative perimeter of a set or of a partition. And this is a bit of computation of shape derivatives, but the idea is that you basically need to perturb your domain at the places where your optimal set or partition touch the boundary, and which are illustrated in the figures below. And once you have the sensitivity, you can launch the optimization algorithm. Here you have the optimization which was done in dimension 2, and you see that the optimal set obtained was the disk. I guess here it was a constraint of 0.25 of the small set has a quarter measure of the big set. And you can see the evolution of the objective function. So it stabilizes. We seem to have reached a maximum, or at least a local maximum. Now, again, talking a bit about the code, the idea is that you need to define the initialization and the parameters for your radial function. Then you have you build the objective function, which depends on the parameters p. Build the mesh, the finite element spaces, and the matrices which are involved in the computation. Then I need to build the function that are needed for NLOP BFGS. You need again the gradient and the objective function. And again, I construct a function for the projection on the constraint. So it is very nice that FreeFEM allows you to construct functions and functions in functions. So it all works very nice. You compute the shape derivative using the results obtained from the optimization and the gradient, and you just perform then an optimization algorithm for this objective function. And sometimes in 3D, it is useful to do a mesh refinement and interpolation, which can speed up the computations, since you start from a coarse mesh and then interpolate on a finer mesh. So these are some examples of the gradient flow optimization in 2D for a partition. You can see that how the shape evolves and in the end arrives to a disk. Here are some results for one phase in dimension 2 and 3. You can see that again, these are the optimization results. So it seemed that for every proportion of the volume of the cell inside, the solution seems to be the ball. These are examples for partitions in 2D with equal areas and different areas here below. And then going quickly, this is also the 3D case. So where you see that it seems that the ball also maximizes the perimeter, of the minimal perimeter of the partition in 3D and on surfaces. And I have a little movie on surfaces. So this is how the shape evolves in FreeFEM. You just build a mesh at every iteration, compute the optimal partition, and then evolve using the shape derivative, and going towards the end, you arrive basically at a ball. So in order to conclude the results of the simulation for this part, it seemed that the ball or the sphere is the maximizer for the functional that we are interested in, regardless of the size of the volume constraint, which is interesting and maybe will give some ideas for theoretical studies. So I just want to say that FreeFEM is a powerful tool for doing shape optimization from application point of view, but also for academic applications. And it's very nice that it now has capabilities to do not only 2D, but also 3D and surface meshing. It's really nice that there are some powerful optimization library that are already included. And I want to thank you for your attention, and I hope that you find this. I want to thank also the developers of FreeFEM for this nice work, and the fact that it really gives a nice tool for doing shape optimization problems easy, and allows us to focus more on the mathematical part rather than on the coding part.
So thank you, Benjamin. There are some questions on this talk.
I have one small question. I didn't understand why you needed to switch between IPOpt and NLOpt. Could you just?
Yes, but NLOpt was used when I did not do constraint optimization. So in this case, if I project the gradient, I do not need to do constraint optimization. I just do unconstrained optimization, and this is faster than IPOpt.
Okay, but because I think IPOpt can also do non-constraint optimization.
Yes, I tried that, but it's faster. NLOpt
okay.
Is faster.
Okay, thank you.
Okay, in fact, I want to have the same question. Because if my memory is good, in NLOpt, when you use matrices, they use full matrices. So it means that the size of your parameter must be not too big. So,
yes.
So maybe in this case, what is the size of your parameters? It's what the size of P, in fact.
Yeah, in 3D, I guess I did like 20,000 nodes. So the size is like 20,000 for NLOpt.
Okay, so
but I remember doing some tests, and I started with IPOpt, and when I switched to NLOpt, it was faster.
Okay.
I don't know why, but yeah.
Me too. But it is one of the advantage of FreeFEM. You can test a lot of methods.
Yeah.
And I think you can also try with Tao in parallel now. And so thanks to the Pierre Jolivet.
Yeah, it's a nice idea. Yes.
Things. But of course, in parallel, it must be a little bit more difficult. Okay, so thanks again, Benjamin. What?
Can I ask one question? Is how about the initial condition for optimization? It depends on the initial, or NLP optimized to perfectly independent of the initial condition?
Yeah, in dimension 2, the initialization is random, so it works very nice for random initialization. But in order not to get a local minimum, I do like 10 runs of NLOpt for every. So I do like 10 initialization and do 10 optimization.
Thank you. That's become clear. Thank you.